All right, so we talked about mirrors, that is flat, concave, and convex mirrors. And now let's talk about lenses, because now we're talking about how light refracts as it passes through different mediums. So we're going to assume that these lenses are made of a material that's different than air, maybe glass. Let's just assume it's glass. So how do I figure out how these images are formed as light passes through lenses? So the steps to draw our rays are kind of the same. What's going to happen is we're going to follow the same steps for our three rays, except now instead of reflecting off the mirror, they're going to refract through the lens. And instead of our eye being over here, looking at the mirror for some image, now our eye is going to be, freaking out a little bit. Now our eye is going to be over here, looking at an object that's on the other side. So we're looking for the image of whatever we're looking at through this lens. So let's figure out how do we do that. So our first ray has to begin parallel to the principal axis and hit the lens. So let's do that real quick. From the tip of the object, parallel to the principal axis, and it hits the mirror, or not the mirror, the lens, like so. Then for a mirror, it reflects back through the focal point. But now, it's going to refract and go through the focal point on the opposite side. So the light is going to bend, and from that point go through F, like so. That's our first ray. Now, I said all of our rays are going to be pretty much the same, but the second one's a little bit different. It went through the center of curvature on a mirror, but there really isn't a center of curvature for a lens, because both sides of my lens for this convex type are jutting outward, and so the center is actually inside. So what's going to happen is, if our ray, the second ray, is supposed to go to the center, it's going to go through the center of the lens, and if it does that, it does not refract. So just go straight through the center, like so. Let me fix that a little bit. Right there, okay. Now our third ray has to go through the focal point first and then run parallel to the principal axis. So since it needs to go through the focal point first, we're going to, I don't want that color, I want this one. It needs to go through F before it hits the mirror. Make sure this is coming from the top of our object. It goes through F, hits the mirror, and then refracts parallel to the principal axis, like so. So where does our image form? Well, our image, if all these rays came from the top of our object, they meet at the top of the image. So our image is extremely tiny. It looks like this, and it's inverted. So if my eyes were over here, that's a weird eye, but you get it. If my eye was over here looking at this, it would see, if I was looking at this object that's upright on the other side, it would see an image that's inverted and extremely tiny on the same side that you're observing from. So, how does the location and everything work for this? So we'll talk about orientation and size first, because those are easiest. The orientation is inverted. The size is smaller than the object. The location is on the opposite side of the object, which is on the same side that you're looking at it from. So if that's the case, this is going to be a real image. If it's on the opposite side of the object, we say that is a real image. So it's kind of like the opposite of a mirror in that sense. Let's move. So again, let's draw our 3 rays. We start at the top of the object, we run parallel to the lens, then as it moves through the lens, it refracts through F. And let me adjust my line real quick. Like so. The second one needs to go straight through the center of the mirror, and it doesn't refract if it does that. So there's the center. Make sure this comes from the same point. Boom. Right through the center, like so. Then the last one needs to go through F first. Hit the mirror, and then run parallel. But I need to fix this for a second. Just come up a hair. Right there. All right, then refracts parallel. Sort of like so. Make sure that's parallel. Okay, so it may look a little off if we don't draw our rays exactly parallel or through F or the center. But what's supposed to happen, just like with case 2 on a mirror, the object was at the center of curvature. So it reflected in the same spot, and it was the same size, just inverted. The same thing happens here. My image should be the exact same distance away on the other side, and it should be inverted, and it should be the same size. So if your rays didn't show that, make sure you know what it's supposed to look like, so you don't get that wrong on the test if you're using this for a reference. All right, so what does our information over here look like? The location is on the opposite side of object, or the same side that you're looking at it. The orientation is inverted. The size is the same, and the image type here is real. Let's move on. So our first ray here starts parallel. Let me fix this for a second. Starts there, parallel. Okay, then it refracts through F on the other side. So let's do that. And again, I need to fix this. Boom. Our second one goes straight through the center of the lens. So let's do that. And fix it real quick. Straight through the center. And then our last one goes through F first. And then refracts parallel. So F right there, and then refracts parallel to the principal axis. If I move that, there we go. So where's our image? So the top of our image should be where these points meet. So our image looks like this. And so now let's fill in our information. So the image is still on the opposite side of the object. The orientation is inverted. The size is bigger or larger now, and the image type is still real. Now let's move on to case 4. Our first ray comes in parallel to the lens, parallel to the axis, and hits the lens, and passes through. Let me make this as parallel as possible. And then refracts through F. So let me fix that. There we go. The second one goes straight through the center of the mirror, like the center of the lens, my fault, like so. So we may be already seeing a problem here, that those two rays, as they refract through, are never going to intersect. So that may tell us we have to do something here. Then our third ray, since it's inside the focal point, we're going to draw it as if it came from the focal point, pass through the top of the object, like so, and then refracts parallel. So again, I see the problem that these are not going to intersect on the right side of this lens. Let me make this parallel. So what does that mean we have to do? Well, we backtraced reflected rays on mirrors. Now let's backtrace our refracted rays for a lens. I'm going to do that with my blue one first. The refracted ray is this parallel one, so I'm going to backtrace that refracted ray. And I'm going to try to do it as straight as possible here. You could do this with a ruler. A ruler won't work on my iPad for some reason. So there's the blue ray backtraced. The red one will look like that pretty much. And as long as we get the gist of this, it's okay. And then the green one would look like this backtraced. So I do see where these intersect now. They intersect here at this point. So that means my image looks like this. And it's actually behind the object, which is weird to think about. So let's fill in our information over here on the right-hand side. Our location is the same side as the object. The orientation is upright. The size is larger. And if it's the same side of the object, if the image type is real when it's on the other side, if it's on the same side, it is a virtual image. And the good way to tell about if it's a virtual image or not is, did I have to do this backtracing to get it? If I did have to do backtracing, that is a virtual image. Let's move on to the last one. All right, so here we have a concave lens, and I can see that because the lens caves in, and that's where the light shines through into the cave. So let's talk about the rays for this one. So our first one is going to, make sure I got the right color here, start parallel, like so. It's not bad, but I need to fix that for a second. Then it's going to refract. But notice how the other lens kind of bent the light towards each other. What a concave lens, or sometimes called diverging lens, does is the opposite. So if the light was going to refract through F like this on a converging lens or a convex lens, which is the first four cases, it's pretty much going to do the opposite here. So it's going to refract, but it's going to refract kind of this way. And how do I know which way that is exactly? Well, I draw the line, and don't draw the line until I'm completely done, as if it came through the focal point from the same side. So it's going to refract at that angle, if I can get this correct. Like so. So the refracted ray looks like that. Our ray through the center, since it doesn't really refract moving through the center, is the same. So we can go ahead and draw that. It's going to be our green ray here, straight through the center. Let me make sure I have this lined up correctly. Boom, like so. And then our third ray is drawn slightly different for this case. So to get an accurate depiction of where the image is, I'm going to draw my third ray. It needs to go through the focal point, but it needs to go through the focal point, on the opposite side of the mirror. So don't draw this until I'm done. I'm going to draw it like it's going through F on the other side. But I know that once it does that, it refracts parallel. So our refracted ray is going to look like this. So now I can move this back, and this is what it should look like. Like it's going through F, it refracts parallel. So again, on the right side, I don't see any of these going to be intersecting, so let's backtrace our refracted rays. The red one, backtrace, kind of looks like something like that through F. The blue one backtraced looks like that. And then if I backtrace the green one, I backtrace it on itself. So I see where this image forms. The top of the image is where all three intersect. So my image looks like that. So as far as our information over here, it's the same side as the object. Its orientation is upright, except this time, unlike case 4, it is smaller. And so the image type, since we had to backtrace, is virtual. All right. Now that we've talked about our cases, let's talk about the equation real quick. All right, so looking at our lens equation practice, we noticed that the lens equation and the magnification is the exact same as a mirror. It's just what do I put in for object distance, image distance, focal length. Are they positive, negative? Let's sort that out right now. So, number 1, blank is always positive no matter what lens is used. DO is always positive for mirrors and images. So, sorry, for mirrors and lenses. 2, blank is positive if the image is real. So our object distance is positive if the image is real. Our image distance is negative if the image is virtual. Sorry, 2 and 3 are image distance. The focal length is going to be positive for a converging lens, and the focal length is going to be negative for a diverging lens. Now remember, converging lens is convex, and it looks like this. Diverging lens is concave, and that looks like this. 6, blank and blank heights are positive when measured upward from the principal axis and negative. So it already has heights, so object and image heights are positive when measured up, negative when measured down. Blank is positive for an upright image and negative for an inverted image. So our magnification is positive or negative depending on the orientation. So hopefully these help with part B when we actually get to use this equation. And again, probably by tomorrow, Tuesday, I will have a key for some of these made, kind of going through the process of identifying the information and a little bit of using it and working it out. So I hope this video was helpful.